That, Aaron, your question would have been a good one to put on. All right, welcome back, everyone. We're at Lecture 17, Math 131. At some part of class last time, we were looking at problem number 25 on page 455, and we worked it two ways, looked like two different answers, and at that particular moment, I was not exactly sure where the mistake, what looked like a mistake was, and didn't want to waste any more time trying to figure it out, but it's a simple fix, and we'll look at that. We've looked at Riemann sums a little bit, and when we think of Riemann sums, we're looking at ways to approximate a definite integral is really what it is, and we divide the region up into little rectangles and add up the areas. We barely touched on that last time. We're going to do a little better today. I relate 6.2 and 6.3 Riemann sums and areas under the curve using the definite integral. Then, after we do this, I want to jump to 9.3 because 9.3 is using the definite integral when you had to integrate using substitution method. So this will send us back to a little bit of drill again with integration by substitution. And then hopefully we have time after that. I'm going to start at 6.3 and pick some even problems and work backwards. Okay? And hopefully tomorrow we'll have some specific questions with your work that we can put up and edit. All right, so let's first revisit page 455, number 25. And I rewrote it from last time. The problem was the integral of 1 over x, natural log of x squared dx. And the way I worked it was I rewrote it as 1 over x times 1 over natural log x squared. Use my properties of logarithms to make it look easy. I let my u be natural log x, so it came out to be 1/2 1 over u du. And here's what my answer looks like. Okay? We already have that in your notes from last time, I think. Then another person in here didn't use the properties of logarithms and said, well, let's let u be log of x, natural log of x squared. So the derivative of that's 1 over x squared times 2x, which simplifies to du equals 2 over x dx, or 1/2 du is 1 over x dx. So we had 1 over the u, 1/2 du. So when we got right here, they look the same. But when we looked back, u is natural log of x squared, or u is natural log of x. So when you get to this spot, you go, whoa, these things, we have not missed any rules. They look different. No way can they be the same. All right. Well, yes, they can. They can differ by a constant. Here's the part that sends you to here. We remember at this point that natural log of x squared by the properties of logarithms is 1/2 natural log absolute value 2 log x plus c. And your properties of logarithms say that when you have a product 2 times log x, it will be 1/2 times the log of 2. I don't need to use absolute values with 2 because it's a positive number anyway, plus the log of the natural absolute value of natural log x plus c. So right here I'm using my properties of logarithms. The log of a times b is the log of a times plus the log of b. Okay, when you distribute your 1/2, you're going to get 1/2 the natural log of 2. Well, that's just a constant, correct? So this part right here plus this c goes into some other constant c that's over here. And so you're now left with 1/2 log absolute value log x plus c. So those are good things to have happened on tape so that I can point out to you that sometimes your answer may not match exactly the back of the book, but you want to check, you know, hopefully the difference between your answer and the back of the book really is only some constant c there, and that's applying your properties of logarithms. Okay, I'm glad you did it that way so we could do this. Everybody good? So don't panic if you're not totally like the back of the book. If you know you've done things right, there's probably a property in there that's going to work for you. All right. So just that 1/2 natural log of 2, that's some constant plus some constant c here. Those two things added together just equals some other c right there. All right. Can we move off that? Good. Okay. All right. That was fun, wasn't it? All right. Let's go back to Riemann sums. We're in section 6.1 and 6.2. We barely did any of it. Excuse me, 6.2 and 6.3, I think it is. We're going to look at Riemann sums and the definite integral. Okay, first thing we're going to do is Riemann sums, and I'm just going to remind you this is in a way to approximate a definite integral. Now the example that I picked last time gave me an exact value for the definite integral because I was very careful to do that. And you're asking, well, why would we take some function, f of x, go from a to b, divide it up into a lot of little rectangles of equal width. Those are equal width in case you can't tell. Equal width, and sum up all the heights times delta x when I told you that the value of the definite integral from a to b, f of x dx, would it give me exactly that area? So your question is, why would you use Riemann sums if you could evaluate the definite integral? Well, for two things. One, you can't always integrate a function. We have very carefully selected functions. There are plenty of functions that can't be integrated. So what you would do is you would use a mathematical software. You put your function in, divide it into 10,000 little rectangles of equal width, and approximate the area that way. And there's also two other ways besides Riemann sums. One, this makes little rectangles. Riemann sums make little rectangles. Another way you can approximate the area is to make little trapezoids. Trapezoids instead of little rectangles. And then another way to approximate, that's called trapezoidal rule. And another way is called little Simpson's rule, where you make little parabolas on top. Make little parabolas on top. It's called Simpson's rule. We only do Riemann sums here. Okay, but also the basis for integration, the definite integral, comes from Riemann sums, where you're summing up from a to b all the heights, because your y value is f of x, all your heights times your little widths dx. So that's the basis for the fundamental theorem of calculus anyway. You're letting the little widths approach 0, dx approach 0. Okay? All right, so Riemann sums, little rectangles. We're going to do a different problem, and last time we only did a midpoint with Riemann sums, but you can do midpoint, left point, right point, and we're going to do all those today. All right, so we'll take an example such as, we can use anything we want. We're just going to pick f of x, which is our y value, equals x squared plus 1. And we're going to use Riemann sums to approximate the area under the curve. I want to go back and talk about those words because I think that's kind of a vague word. Words, area under the curve. From x equal 1 to x equal 4. X equal 4. And I'm just going to pick n equal to 3, meaning 3 subintervals. 3 subintervals. 3 subintervals. That's a SUB. Woo, 3 subintervals. All right, area under the curve is generally understood to mean we have a continuous function. You can only do this for continuous functions over that interval anyway, from x equal 1 to 4. It's got to be continuous, or how else would you divide it up into little rectangles, right? So you got to have a continuous function. Under the curve generally means from the curve to the x-axis. Under the curve. Your book will call it find the area under the curve. Under the curve. Actually, a better question, wording, I think, would be to say find the area between this curve and the x-axis instead of just saying under the curve. All right, so just wanted to make that clear. Some books don't even use the words area under the curve. All right, so let's get a visual of what's going on here. And I'm going to make it really big because I need to be able to see my little areas here. All right, y equals x squared plus 1. We know that's a parabola that just opens up. Parabola that just opens up. And the y-intercept is at 1, right? But I'm only going to look from 1 to 4. 1 to 4. So when x is 1, the y value is 2. So I'm just going to draw it like this. And when x is 4, the y value is 17. Just spreading this way out so we can see it. All right, this is definitely not drawn to scale, but it's going to help us use Riemann sums. All right, the first thing we're going to do is we'll go ahead and do left point. Your book will say use left point or right point. Oops, I get this mixed up with the Maple software. Some call it left point, right point. I believe this is called left sum, right sum. Sorry. Software will call it left point, right point, midpoint, and this calls it left and right. Doesn't call it either one. Midpoint, left endpoint, right. Okay, they call it left endpoint, right endpoint, midpoint. And so here we go, left point. All right, the Maple software, you type in left point to mean left endpoint. Okay, all right, we're going to use left point. In subintervals, so we want to find the widths. So delta x is going to be your b minus your a, 4 minus 1. This is the b, this is the a. Divided by the number of subintervals, 3 over 3. And I just try to do kind of easy stuff. Delta x is 1. So I'm going to divide this up into 3 subintervals of equal width. Here's your delta x here. Okay. All right. So we're going to sum up all the heights times the widths. That's widths. Okay. But we're going to use the left point, the left, to find the height. All right, so let's go to our, what I like to tell students is, let's go to our first interval and put your hands there. Go to your first interval, put your hands. If we're doing left, find your left hand. That is where you're going to find the height and carry it to the right hand. The left hand is the only one moving. Okay? So when you use your left hand, here's your height, and it's going to come over to here. This is using your left going to your right. All right, your y value, as you remember, is x squared plus 1. So the height, which is right here, is y equals x value is 1, 1 squared plus 1, or 2. So the area of this little rectangle is height, which is 2 times width, which is 1. So 2 times 1 plus. Everybody see that? All right, let's go to the next subinterval. If you'll put your hands on the interval, you're doing left, so only the left hand gets to move. And the left to draw across has to come to the right. So you get your y value from your left hand. So from the left hand, here's the y value. And the left hand comes across to the right. Clap it. Be happy. Clap. Claps to the right. All right, so we have to get this y value. So y is equal to 2 squared plus 1, which is 5. So this height is 5. The width is 1, so the area of this one is 5 times 1. Okay. And now let's go to the next little part. We go find our interval. It's left, so the left hand is the only thing moving. We find the height based on the left. Find that dot. Oops, I wanted to do that in a different color. Where's blue? Left, and take your left hand and clap it to your right. Send it over. That's a rectangle. And that height is y equals 3 squared plus 1, or 10. So this is a 10 by 1. Okay, so the approximate area then. Now, just looking at this, here's your curve. You want the area under this curve. Would you think this estimate's going to be pretty low? Yeah, you're leaving out this space, and this space. So in this case, and this is because it's increasing concave up, by the way, you could study, you could analyze which of these methods gives you the better area, and it has to do with the concavity of your curve. I just thought I'd give you that tidbit of information. This is the area right here you're looking at. This area and this area. But you're really trying to approximate all of this area from here all the way down. So you see you've got several regions there that's left out. So you know this is going to be a way underestimate of what the real area is. Let's add that up. That's 17, it's approximately 17 square units. Now, how could I, if I wanted to use left endpoints, improve this greatly? How could I improve this approximation greatly? Yeah, put a whole lot more rectangles in there. Delta x of 1 is pretty wide. Okay, I just did it so our arithmetic would be easier. Okay, let's do right endpoints. Right endpoints. Y, which is our function, equals x squared plus 1. We're going to do right endpoints. And personally, I can just see it so much better when I draw it. Okay. All right, we're going to approximate that area. And this is using Riemann sums, and we're going to continue to use n equal 3 because n equal 3. All right, why don't you do this? Get your little interval. Which hand's going to move? Right, because you're doing right endpoints. Okay, go for it. Take you about 3 seconds. What's that come out to be? 32. Whew, that's way different than the other. That's approximately 32 square units. All right, and in this case, you see you're way over your estimate because you're trying to find the area under this curve, and you got all these big sections sitting right here. All right, everybody good on that? All right, let's try midpoint. Midpoint's going to actually give you a better estimate here because of the shape of my curve. All right, any questions on this? You go, your right hand finds the y value and claps to the left, comes across to the left. Find your right hand in the next interval, carried across to the left. Find your y value. Find the y value on your left hand and come across to your left.
Question. So on our test, are we gonna have to know, like, just pick which one works best?
Oh no, I tell you.
Oh, okay.
I'm going to say the question was on a test. Are you supposed to figure out on your own whether you use right, left, or midpoint? No, I'll be very specific and I'll tell you in and give you the function.
Oh.
All right, everybody good? All right. Go for midpoint. What are you going to do when you do midpoint?
Find the height of the middle.
Go to the middle and like make a T. Make a T. Go to the middle and make a T on your interval. So we go to the middle and it's like making a T over your interval. I call that a T. I don't know what. Maybe a goal post. That's what it is. Goal post. Football goal post. All right, so this would be y equals 3/2 squared plus 1. What's that, 13/4? 9/4 plus 4/4, 13/4. Okay? All right, next one is go to the middle and come straight across over the entire interval. (29/4), I think, for the height. And you can already tell this is going to be better because you might be including a little bit, but you're leaving out a little bit. So they're going to match up pretty closely. We got 53/4. Okay. All right, so the area is approximately 13/4 plus 29/4 plus 53/4. Thank you. And what does that come out to be when you do the long division? 23.75 is approximately. And just visually, we can look at it and tell that was better. But even for right sum and left sum, if we'd let n be 1,000 subdivisions, it would have been right on top of what the area actually is. Now, this is still an approximation. Okay, we've got still some error in here, I'm sure. All right, everybody good on this? Let's use the definite integral to find the exact area. Okay, I carefully picked something that we know how to integrate. All right, So using integration, since we know how, we can find the exact area using the definite integral. So we would integrate from 1 to 4, right? And how do we represent the height of all of our rectangles? X squared plus 1 times the width of all of our rectangles, dx. That's height times width. We're summing up all the little rectangles from 1 to 4 whose heights are x squared plus 1 and widths are dx. Okay, let's integrate this, and this will give us exact area. All right, if you integrate x squared, I guess that would be x cubed over 3. What is it you get when you integrate 1? X. And we saw you don't have to put this plus c in there because it's going to cancel out, but you can if you want to. We'll evaluate from x equal 1 to x equal to 4. What was the question? Yeah, I'm using the rule x to the r, add 1, divide by 1. You could do that as a x to the 0. Okay, and when we evaluate its upper value, so that would be 4 cubed over 3 plus 4, minus lower value, 1/3 plus 1. Okay, 4 times 4, 64 thirds. Plus 4 minus 1/3 minus 1 would be 63 thirds plus 3. 21 plus 3, 24 square units. 24 square units. And using midpoint, we got what, 23.75? All right, so we were pretty close even with that wide delta x of 1 when we use midpoint. And again, that was because that was an increasing concave up curve. That just works well for midpoints. All right, everybody good? Okay. Questions? All right, I have a definite integral I would like for you to evaluate. I have a reason for you doing this. I'm leading somewhere. Evaluate. The instructions are just evaluate. Evaluate this definite integral from 0 to 2, x minus 1 dx. And tell me what you get. What'd you get? Okay. When you integrate this, you're going to get 0. When you integrate, you get x squared over 2 minus x, evaluated from x equals 0 to x equal to 2. 2 squared over, which is 4. 4 over 2 is 2. 2 minus 2 minus 0, and you get 0. So you're asking yourself, well, what is going on here? Because I have been saying to you, we're summing up all the little areas where this represents the height and this represents the width. Let's get a visual on this. Let's get a visual. What does the graph of y equals x minus 1 look like? Straight line, y-intercept is at -1. Okay, and you go up 1 over 1. And so the line looks like this if we were going from 0 to 2. Okay? So when we evaluate a definite integral, it's not taking into consideration if the curve is really up above the x-axis or below the x-axis, because you're summing up y values, and all the y values from x equal to 0 to 1 are negative, and all the y values from 1 to 2 are positive. So if you simply integrate a definite integral, it is going to give you what we call net area. Net area. It will take all the area above the curve, above the x-axis, and call it positive. All the area below the x-axis, it calls it negative, and it adds positives and negatives, and it nets out. This, if your test question says evaluate a definite integral, I call this my Nike commercial. Check. What does the Nike commercial say? Just do it. Don't worry about where the curve is, and you will know that your answer is giving you a net area. If it's positive, you know that for that curve, there's more area above than below the x-axis. If it comes out to be negative, if you needed to know it or look at it, you have more area below than above. If it comes out to be 0, they just balanced each other out, and you have the same below or above. Now, that's one way to ask a question. Just evaluate a definite integral. Another way would say, use the definite integral to find the area between y equals x minus 1 and the x-axis. Okay, find the area. Don't give me a net area, but find the area. Okay, well with that you need a visual, because this is below the x-axis, and if you just use y times, you're getting a negative y. So what we will do is, this is what I do. I come in and draw a little element, you know, like a little area, a little rectangle that I'd be adding up, little rectangle. And if I were going to tell the height, let's just go on the y-axis here. If I'm at y equal to 0 and y equal -1, 0 and -1, how tall is this in between 0 and -1? 1 unit. Wouldn't you say top minus -1? So when you're getting the heights of any of the little rectangles in here, it's going to be the top number, because that's the biggest, minus the bottom, right? It's always going to be top minus bottom. So if we wanted to use the definite, I forgot to use the word integral in there, sorry, use the definite integral to find that area, I would first use it for the first little region, and I would say I'm going to sum up from -1 to 0. And all my heights, well, what's the equation for this top line right here, the x-axis? Y equal to 0. So y equal to 0 is on the top of my curve. The bottom of my curve is x minus 1. So we'd say top, which is 0, minus the bottom. So that gives me how tall any little rectangle I put in there is, dx. Top minus bottom. And then I would pick up at 1 and go to 2, and the top curve is x minus 1. What's the bottom curve really? 0. So we've been really doing that without telling you. Dx. I ran out of space there. Can you get that? Dx. Okay? All right, let's finish this and just show you that that's going to give you actually the area between that curve and the x-axis. All right, so when the problem says use the definite integral to find the area, you got to have a visual so that you'll know how to find the height of any of those rectangles between the curve and the x-axis. So if you're below the x-axis, you have to do top minus bottom. Same thing here is really top minus bottom. All right, let's finish it just so you see that's what it is. All right, and by geometry, we already know the answer, right? The base is 1 unit, and the height here, when x is 2, is 1. So this area is 1/2 times 1 times 1. That's a half. So my answer should come out to be a positive 1 if I add those two areas together, because we don't really talk about negative areas. Okay? All right, so let's just do it. So we integrate from -1 to 0. Don't forget to distribute negative x plus 1 dx plus the integral from 1 to 2 x minus 1 dx. All right, so if we integrate over here, we get minus x squared over 2 plus x, evaluated from x equal -1 to x equal to 0. And I'm going to substitute in, so it's minus 0 squared over 2 plus 0. Minus, now we're going to put in -1. Remember, it's only the x here that's squared, and then it's minus, so it's like minus 1 squared over 2 plus -1. So we get 0 minus, all right, -1 squared is positive 1. Then we got the minus on the outside, -1/2 minus 1. And that is going to give me, did I get those, did I do that right? 2 minus 1. -1. Yes. -1/2 minus 1. Okay, so that's going to give me positive 3/2. Did I do my area wrong here? All right, let me keep going. All right, so over here we have x squared over 2 minus x, evaluate from 1 to 2. 2 squared is 4. 4 divided by 2 is 2 minus 2 minus 1/2 minus 1. Oh, we're going to work out good here. I was concerned I wasn't. 0 minus a minus 1/2. Oops. And that's going to be positive 1/2. When you add 3/2 plus 1/2 together, that's going to equal 1, which is what we came up to be the area with those two triangles added together. Okay, the definite integral gives you a net area. Did I do something wrong? Yes. Where is it?
Second to last line. Why is it a -1/2?
Why is it a -1/2? Right here?
Yeah.
Because
The
it's the -1 that's squared. This is not, let me put our orange marker on here. This is not equal to minus x quantity squared. It's the x that's squared and then the -1. The exponent only goes with the variable it's next to. This is not parentheses minus x squared. It's minus and then your x, and my x happened to be a -1. It is -3/2, but minus a -3/2 is positive 3/2.
Oh, you put that, okay.
Distribute your negative right there. Okay? All right, let me say from the top what I just was trying to point out pretty quickly to you here. Everybody got that? All right, anytime that you see evaluate a definite integral, you're just going to do it. That's your Nike commercial. And if that comes out to be positive, it just means that this curve with respect to the x-axis. If it's positive, there's more of the curve above the x-axis than below. If it comes out to be negative, it meant that more of the curve was below the x-axis than above, because it's summing up all the y values, and you got some y values that are negative in there times heights, times widths dx. If it comes out to be 0, it just means they net each other out. If you were going to use we have an application of the definite integral. If you were going to use that definite integral to find the area between y equals x minus 1 and the x-axis, we need a visual. 3/2 plus a half. Hold on till I get there. Okay, here's the curve y equals x minus 1. We would evaluate from, whoa, here's my mistake. Yeah, we're summing up. Is that what you were asking? 0 to 1. Whoa, bad. Bad. We're summing up with respect to x. X goes from 0 to 1, not over y, negative 1 to 0. I'm sorry, bad, bad, bad. And then we picked up from 1 to 2. Let me go back in here. Bad, bad. Let me rewrite it. We're going from 0 to 1. 0 minus x minus 1 dx plus the integral from 1 to 2 x minus 1 minus 0 dx. All right. Actually, this sometimes happens on tests. I can't believe I did that. All right. Remember, you're integrating with respect to x, and x ranges from 0 to 1. We're not worried about the y values going in. Was that what your question was, that you were politely trying to ask? All right. So x ranges from 0 to 1. Height of rectangles, top curve minus bottom, because the height from here, 0 to minus 1, would be 0 minus a negative 1 would give you the 1 unit. So top minus bottom. And then we pick up from 1 to 2. Let me redo that real fast. We integrate from 0 to 1 minus x plus 1 dx. When you integrate, you get minus x squared over 2 plus x, evaluated from x equals 0 to x equal to 1. Now this was where your question was, putting in that minus.
Well, it doesn't really count anymore. What I was confused was when we had the negative 1, and it was negative times negative 1 squared. I thought the two negatives would cancel out to make it
Okay, I'll come right back to that. Hold on. Okay, so now we substitute in. Remember that minus x squared really means to square the x and then put the minus with it. So you get minus, and if you'll put a 1 squared in over 2 plus 1. Minus a minus 0 squared over 2 plus 0. So 1 squared is positive 1, but now you got the minus out there, so that's negative 1/2 plus 1, which is 1/2. And then we work this side correctly down. That was 1/2. When you add those two together, that gave you a total area of 1/2 plus a half, 1 square unit. I just looked out that I worked it incorrectly and got the right answer. But I would not have gotten credit because we grade work, not just answers. So I got a bad deal on that one. All right. Let me go back to what your question was. Your concerns were right in here, I think.
It's right there, where it says negative times negative 1 squared.
Right.
I thought the two negatives would cancel out.
Exponents
I just
come
realized-
before. You have to handle exponents first. So it would be minus 1 squared, which is positive 1, and then minus a positive 1. Okay? But that was part of a bad question. I did it bad. All right. What do y'all want to give me? A minus 10 on that or what? Minus 10. Bad. Okay. Minus 100. I'll remember that when I'm grading your paper. All righty. All right, let's try one more of these with the area, the just do it and the area. So just do it in the area. All right. Anybody want to make it up? Let me just find one in the book. Then you'll know this is coming right out of the book. I don't see one I like, so I'll just make it up. Okay. Evaluate. Test question. The integral from 1 to 4 of x squared minus 4 dx. Okay? All right. Here's the test question. Evaluate the definite integral from 1 to 4 x squared minus 4 dx. What are you going to do? This is your Nike commercial. Just do it and you don't care what it looks like. How am I doing? Better?
Yeah.
Okay, that looks like 63 thirds minus 12. 21 thirds minus 36 thirds is 15 thirds. Minus 15 thirds minus 5. Oh, 21. Oh, 21 minus 12. Okay. Should I tell everybody who's watching this that I was been up since 4 o'clock this morning? I'm sorry. All right. 63 thirds. Not having a functioning brain here. Sorry. 63 over 3 is 21. Minus 12 comes out to be 9. Is that right? Thank you. Thank you. You just right. When you're just evaluating, you integrate and evaluate top number minus bottom number. All right. And really, in order to do this, this curve in here has to be continuous over that interval, and it is continuous. Okay. All right. Let's change the question. Everybody good? 9. All right. We want to find the area. That means we want the exact area. It doesn't mean go to Riemann sums. The area from x equals 1 to x equals 4 of the region between y equals x squared minus 4 and the x-axis. All right, do you see the difference in this question? Find the area. The area. All right, so we need a visual here. See what's going on. y equals x squared minus 4, you know, is a parabola. The y-intercept is negative 4. And we're going to start at 1. So when x is 1, the y value is negative 3. So this is the point 1, negative 3. And it's going to go to x at 4. 16 minus 4 sounds like a 12 to me. So this would be the point 4, 12. And we know it's going to go through here at 2. So the graph, this is a curve, but it's going like this. That's the 2 right there. We know it has y-intercepts 2 and negative 2 if you're putting the parabola in there. 2 and negative 2. All right. So we want to actually figure out this area right here and this area right here. Okay? Get the areas. All right. Well, the part from 2 to 4 is going to be real easy, correct? So let's do that little part first. We just put in a little, these, by the way, I called it this. I didn't tell you what I said. Element of area. You want to put in a little element of area because then that way you can tell which curve is on top and which curve is on bottom. What's this bottom curve called? Y equals 0. And the top curve here is y equals x squared minus 4. So anytime you have a x value between 2 and 4, such as 3, if you want to know how tall this is at 3, it's going to be 3 squared minus 4. It's going to be 9 minus 0. That would give you your height there. Oops, couldn't see. 9 minus 0. All right, so how are we going to find this little area right here, everybody? You're going to integrate from 2 to 4. And how do I represent the height of my curve? X squared minus 4. And I'm just going to put this step in, but a lot of people just leave it out. That's the line y equal to 0, and this is the curve y equals x squared minus 4, so it's always really top curve minus bottom curve. And then the width is dx. Okay? That will give me that area. All right, I'm not going to work this all the way through because I want to get in the book and go through some problems. All right, how about this little area right here? Let's put in the little element of area so you can see your top curve and your bottom curve. You write it down and show your neighbor how you find this little region right in here. And then tell me. Okay, you're going to integrate from what? 1 to 2, because we started at x equal 1. 1 to 2.
Top curve is 0.
Top curve is 0. Don't forget your parentheses in here. Bottom curve is x squared minus 4. And width is dx. So that's top minus bottom. Okay? And when I integrate that, that gives me that area, and it'll be a positive value because all your y's will be positive. See, that's 0 minus your y's. Your y's here would be negative, but minus y is going to make that positive. So that would actually give you the area there.
If we hadn't drawn a visual, how would you know from like what
You are going to want to draw a visual.
as only
Because you need to be able to visualize what your top and bottom is,
right,
and where the intersection is so you know how far to go over.
okay.
And that would be section 6.4, where we really spend a lot of time drawing, finding points of intersection. Okay? All right. That will give us the area. All right, let's start in the book on 6.3 and work backwards with some examples. Page 345. Page 345. Okay, I'm looking at problem number 2 on page 345. It says, set up the definite integral that gives you the area of the shaded region. And I'm going to put somebody's definite integral up so that in case we need to edit it. Number 2, set up the definite integral that gives the area of the shaded region. That was pretty easy after what I just put you through, don't you think? You don't need to work it, you're just setting it up. Okay? The instructions just say set it up. You got yours? He'll give me theirs. You don't have to work it, just set it up. Have you got yours? All right, let's see what yours is. Do you mind?
No.
All right. Let's see if we need to edit this in any way, shape, or form. All right, if I can hold it side by side so we can see here. All right, this says I'm going to sum up from starting at 1 to 3. X goes from 1 to 3. Would everybody give a big old check for that part? Okay. The height of each of these little rectangles that you could put in here is x plus 1 over x, because y gives you the height. So this represents all the heights. And if you technically wanted to, you could say that minus 0. Okay, you could say that minus 0. Now, is anything missing? dx, very important. dx tells you that you're integrating with respect to x, and dx also says this is values of x ranging from 1 to 3, which is what I did wrong in my other problem. So this is heights, and then little dx's is if you divided this into a zillion little rectangles.
No, I made a mistake.
Oh.
1 over x.
I didn't even catch that. You're just looking at it wrong. She had it right. It's x. Thank you, thank you, thank you. Yep. X plus 1 over x. So there's your height. So you could have, if you felt so inclined, write x plus 1 over x minus 0 to get in the habit of saying height, top minus bottom, and then your dx. All right, but this would have been perfect. Okay, everybody good? How many forgot their dx? Raise your hand. Let's have true confessions. I know you were not the only one. Don't worry about it. Okay, pass that back. All right, I'd like for you to go to problem number 32. Problem number 32. We're not going to find the area because you have to integrate. I'm more interested in your setting it up for me. Number 32. Notice that's not a Nike commercial. That is find the area. Find the area. Y equals square root of x from y equals 0 to x equals 4. X equals 0 to x equals 4. Give me yours.
Me?
Mm-hmm. Do you mind? All right, what does the graph of y equals square root of x look like, everybody? You got to have a visual. Yep. So the only thing that I would start out complaining about here is you're just guessing. I'd call this a guess because you're not for sure that the square root of x is always up above the x-axis. Well, you sort of are. But there's the graph of y equals square root of x. And you're going to go from 0 to 4. Okay, so there's your little region. So you're going to sum up from 0 to 4. All the little heights are your y values, square root of x, and widths dx. Would everybody give that a big check? and you kind of looked out because it all was above the x-axis, y-axis, all above the x-axis. So be careful with that. Okay. All right, everybody good? All right. Now, go to number 18. Number 18. The instructions are to calculate the definite integral. Do you care what the picture looks like when it says calculate? No, it just says do it. This is your Nike commercial. So do number 18. Okay, we'll do this one together. Do it. All right. How do we need to rewrite this before we start integrating? Okay. All right. Very good. Very good. So it's 3 times e to the 3t raised to the negative 1 dt. I'm putting in every step. If you'll put in every step, hopefully you won't make mistakes, and hopefully I won't either. How do we deal with this power of a power? Multiply. So we have the integral from natural log 2 to natural log 3, 3 times e to the minus 3t dt. Okay, you have one of 3 forms that's going to fit. U to the r, 1 over u, or e to the u. Definitely an e to the u, isn't it? All right, so let's come over here. What are you going to let u be? Negative 3t. So du is minus 3 dt. Oops, you know what I did? I didn't do like I told you guys to do. The e to the minus 3t is e to the u. Now, what's 3 dt going to be equal to? Yes, negative du. So negative du is 3 dt. So the 3 dt becomes negative, like negative 1 du. All right, so when we integrate, we're going to get minus e to the u. Oops, and I went on and put what the u was. Sorry, I was thinking ahead. Minus 1 e to the minus 3t, and we're going to evaluate from t equal natural log 2 to t equal to natural log 3. Everybody good that far? Let's get one little step. The answer was minus e to the u, where u is minus 3t. You can put the plus c in there, but when you evaluate the definite integral, it's going to cancel out anyway. Everybody good? All right. Now let's get this where we can figure out what it is. I want to get rid of that negative exponent. So that's going to be negative 1 over e to the 3t. And we're evaluating from t equal natural log of 2 to t equal natural log of 3. Do you see why these properties of exponents and negative exponents, they just keep coming up every class period, don't they? It's important that you get it. Are everybody good so far and in agreement with me? All right, so this is going to be minus 1 e to the 3 natural log of 3 minus a minus 1 over e to the 3 natural log 2. Okay, so we put in the upper limit, so it's minus 1 over e 3 natural log of 3 minus a minus 1 over e 3 natural log of 2. All right, how are you going to deal with e to the 3 natural log 3? Yes.
The e with the natural log makes it just 3 cubed.
Almost. Very close. Minus 1 over e to the natural log of 3 cubed, which is what, 27? 3, bring the exponent on the 3. 3 times 3 times 3 is 27. Minus 1 over e to the natural log of 8. Oops, let me get another piece of paper under here. This is a great problem for a test. Why? Because it's got use substitution and it reviews your properties of logarithms. All right, so our exponents and logs. All right, what's e to the natural log of 27 equal to? 27. So we get minus 1 over 27 minus a minus 1 over 8, and whatever this comes out to be. At this second, I don't really care. I just wanted to get that far. Negative 1/27 plus 1/8, whatever it is. All right. Not bad, huh? Let's take it from the top. We knew it was going to be an e to the u problem, so we brought the e to the 3t up to the numerator to a negative 1 power. Properties of exponents means that's minus 3t power of a power. It's a e to the u, so the u is negative 3t, du is minus 3 dt. When you look, you've got a positive 3 dt, so 3 dt is minus 1 du. We're good to right there, correct, everybody? All right, when you integrate e to the u, you're going to get e to the u, so there's your minus e to the u, evaluated from natural log 2 to natural log 3. So we substitute it in. We get the joy of remembering our properties of logarithms. 3 natural log 3 is natural log of 3 cubed, and 3 cubed is 27. 3 log 2 is natural log of 2 cubed, which is natural log 8. Your identity, e to the natural log of a is a, so we get negative 1 over 27 minus a minus 1 over 8, and there we are, and we're good. Any questions on that, now that we did it together? That's what you were telling me to do, right? You're looking at it like you were concerned about something. You're okay? That's what you told me. You were the star. You told me what to do. All right, let's look at problem number 36. Problem number 36. This is page 346, as you can see. We have the graph of g of x given. The question is, if I evaluate from 0 to 7 g of x dx, don't answer out yet, would I expect the value of this definite integral to be positive, negative, or 0? Y'all are too good, because this is my Nike commercial. It says just do it, and that gives me the net area. And if you look at this little area right here and this little area, that seems less than this area right here. So that's positive, positive, negative. Looks like it would come out to be negative. Okay? All right, let's go to problem number 39. Problem number 39. A helicopter is rising straight up in the air. Its velocity at time t is 2t plus 1 feet per second. Feet per second, feet per second. Rate of change, change in feet per second. Everybody got that? How high does the helicopter rise during the first 5 seconds? How high? Okay, that's velocity. You're going to have to integrate to get to distance, right? All right, so two ways we might want to look at this. V of t is really the change in the, if s is distance, change in distance over change in time, and that is equal to 2t plus 1, right? 2t plus 1. And if I anti-differentiate velocity, remember velocity, I took the derivative of the distance function to get to it, so anti-differentiating will give me distance. So when I anti-differentiate, actually it goes like this. This is more than you want to know, but you bring your dt over. If I say I'm taking the derivative of the I'm anti-differentiating change in distance, that gives me distance. All right. Now it says it wants to know, though, exactly during the first 5 seconds. So that would be from time equal to 0 to time equal to 5, from 0 to 5. I'm going to figure that out from 0 to 5. So when I integrate, I get 2t squared over 2 plus t evaluated from t equals 0 to t equal to 5. All right. Is everybody a believer that if I have the velocity function, which is the derivative of distance with respect to time, if I anti-differentiate velocity, I'm back to distance? If you take the derivative of your distance function, you've got velocity, right? So they're going back and forth. So we have, what, t squared plus t from t equals 0 to t equal to 5. And so the total distance it's going to travel during the first 5 seconds is 25 plus 5, 30. I forgot, was this feet? Feet. 30 feet. It's going to travel 30 feet during the first 5 seconds. All right. Everybody a believer on that one? Did I convince you?
Question.
Yes.
Where it says s is equal to 2t squared divided by 2y divided by 2.
Why did I?
Yeah.
If you integrate t to the first, you got to add 1 to it and divide by it. I'm using the formula x to the r. Add 1 to it. The exponent's already 1, so 1 plus 1 is 2, and divide by it. Is that good?
Yeah.
Okay, everybody good? All right. Now the next part's what I really love. The next part says, represent the answer to part A as an area. So what it's going to do is let you use some great critical thinking skills. And you're just going to be so proud of yourself. So here we go. I'm going to quickly graph the velocity function. Here is t, and here is velocity. And they gave me the velocity is 2t plus 1. Velocity is 2t plus 1. So 2t plus 1 looks like this. Velocity equals 2t plus 1. Okay, just a straight line. Constant velocity is pretty much what it is. Okay. All right. If I integrate from 0 to 5, the answer is 30. It traveled a distance of 30 feet. Where on my graph here do I see distance represented? Where would I find 30 feet on my graph? Did I ask that? Excuse me? If x is 5, t is 5, that's 11. Connect these two things. Here's the velocity curve.
The hypotenuse of the right angle triangle. That slant line.
The area under this curve represents distance traveled. If this is your velocity function and you anti-differentiate velocity, you got distance. And if you sum it up from 0 to 5, this area underneath here will represent the distance traveled during the first 5 seconds. Pretty neat, isn't it?
Distance would be area and distance.
Area under this curve, 2t plus 1.
Would be a distance.
It will give you the distance traveled. Because that's a velocity, I plotted time versus velocity. And if you anti-differentiate velocity, you get distance. Anti-differentiating is integrating, and since all that was up above the x-axis, the area under the curve.
But theoretically, integration represents area. That's the area is the area. But practically, when you say distance, it just says something length.
Right. If you were graphing this function right here, which is time versus distance, even though the helicopter is going straight up, you're plotting it against time, and the curve's going like this, even though your helicopter, it's just telling you it starts out slowly and it's going up faster. So this is time versus distance. You know, it measures how far it is up after every few seconds, or whatever this is, seconds. And this represents the velocity function. So this is a derivative, and underneath gives you the total area. It's pretty neat. Hard to believe, but that's it. All right, let's look at another problem, so just see if we can answer the question. Let's look at number 40, for example. After T hours of operation, an assembly line is producing power lawnmowers at a rate of mowers per hour. They're producing, this is the rate that they produce, mowers per hour. So if you wanted the total number of mowers that are produced from that time, this is the mowers per hour. So if you want the total number, what would you do? Anti-differentiate this or integrate from 2 to 5. And that would be area under that curve. Because you would be actually graphing the derivative, so underneath would give you total. Let's look at number 41. Marginal cost function. We already know what marginal cost is. The cost of producing the next item. Marginal cost. This says, that's a derivative. Find the total cost of producing 6 additional units if 2 are currently being produced. So to go from 2 units to 6 units, what's going to be your total cost? How do you go from derivative to cost? Anti-differentiate to get to cost. And you would integrate from 2 to 8, right? 6 additional, 2 to 8. And if you graph the derivative function, the area underneath that would represent that total cost there from 2 to 6. Pretty neat, pretty neat. All right, let's back up. I wanted to hit 6.2, make sure we're good. Play with that. We'll look at it again. 6.2. Let's go to page 334, number 14. Number 14. The exercise is you're supposed to use Riemann sums to approximate the area under this graph, meaning between the curve and the x-axis, And we're supposed to go from 1 to 7. We're going to do problem number 14. 1 to 7, n equal 3, and we're going to do the midpoints of the subinterval. All right, so we're going to go from 1 to 7, and we're going to divide it up into 3 subintervals. So what's going to be the width of each subinterval? 7 minus 1, which is 6. 6 divided by 3 is 2. Okay, so let me see if I can mark off 2 units. So here's the first little subinterval. Here's the next little subinterval. And here's the next. All right, so delta x is going to be equal to 7 minus 1 over 3. 6 divided by 3, which is 2. So the width of each of my little rectangles is going to be 2 units. Everybody see that? All right, and we're supposed to use the midpoint. So go to our first little subinterval from 1 to 3. 1 to 3. So the midpoint there is 2. That looks like that y value there is 7, doesn't it? So there's my first little rectangle. So that area is going to be, what, 7 times 2? 14. Okay, let's go to the next little subinterval from 3 to 5. The midpoint is 4. Oh, looks like its height is still 7, isn't it? Okay, so that area is going to be 7 times 2. And we're going to go to the next little subinterval from 5 to 7. The midpoint is 6. And that little height there looks like it's going to be 4. So we've got 4 times 2. Everybody see how you're getting these? So 14 is 28, and 8 is what, 36? So the approximate area there would be 36 square units. Okay? 36 square units. All right, I think Riemann sums are okay. Don't you? Let's see what 6-1 looks like. Okay, let's, especially because we had a question at the beginning of class, I did. Okay, I'm on page 325. Page 325. And let's look at problem number 42, because we actually haven't done one just like that. Number 42 says the derivative is equal to 2x minus e to the minus x. And we're given a point on the curve that when x is exactly equal to 0, the y value is equal to 1. We're given the derivative, and we are to find the function. All right. How would you start out doing this problem? From the derivative to the function. Anti-differentiate it. All right. So let's do problem number 42. Anti-differentiate that, and I'll catch up with you. This is page 325. Okay, what'd you get when you integrated it? X squared. Good. X squared plus e to the minus x plus c. Perfect. All right. What I did, just in case you wanted to, is you can integrate term by term. So I went the integral of 2x dx plus minus 1 e to the minus x dx. So 2 times x to the first is going to be 2x squared over 2. And this last little part here, I did an internal of my brain u substitution. The u is minus x, du is minus 1 dx. So that minus 1 dx is all my du, so it's an e to the u du. The negative 1 dx is my entire du. So it's an e to the x plus c. Cleans up to right here. So I found all functions, but this said I'm only interested, however, in the one that says when x is 0, y is 1. How's that going to help me here? All right, it's going to let me find c, right? Instead of thousands or 100,000 solutions, I want the one that actually goes through this point. So when x is 0, y is 1, so 1 equals 0 squared plus e to the minus 0 plus c. And what's e to the 0? 1. So I get 1 equals 0 plus 1 plus c. So in my case, c is equal to 0. So the particular function I want is y equals x squared plus e to the minus x.
So it doesn't matter if it's e to the negative 0 or e to the 0, it's just 1.
Yes, e to the minus 0 and e to the 0 is 1. Because e to the minus x is 1 over e to the x. And if you do 1 over e to the 0, that's 1 over 1, so it's still 1. Okay. Thanks for asking that. That's a good point. All right, anybody else question? Are we good? All right, so work before tomorrow. Get your questions together. We're going to do a very important section tomorrow, 6.4. And I forgot to look at 9.3. So we'll do 9.3, and that'll be the end of test number 3. Okay? All right, but let's get questions tomorrow too. All right, have a great day, everybody.